Okay, let's pick back up where we left off with our binary search trees. So it's been a few days since we looked at this because of the weekend. So the first thing I want to do is run our code and kind of refresh where we left off. So let's look at our three classes first, and then we'll run this. So we've got our binary search tree, three classes. This is our first, binary search tree. And in our binary search tree, we're putting Pop-Tarts, Pop-Tart objects. All right, so if we look at the variables, the class fields that we keep for our binary search tree, there's just two. We keep a reference to the root, that is the Pop-Tart that's at the root of the tree, if there is one. We also keep track of the size. That's it. Okay. The other thing that the binary search tree is responsible for is all of the adding, removing, and searching functionality. Okay. So here's our constructor. Sets root to null and size to 0. We have a little helper method that tells us true or false whether or not there is something in the tree. And then the only other thing we did last class was we wrote the add method. And if you recall, we have two add methods. All right? We have the one that gets called initially from the driver. Notice it's public, so we can call it from another class. And then we have a private add method that is recursive. Okay? And what makes it recursive is the fact that it calls itself. There's not a sort of designation that you have to give a function or a method that is recursive. You simply make it so by calling it. All right, so if we take a look at the add method, and this is what gets called from our driver. We create a Pop-Tart object, and we pass it in. First thing we do is we increase the size. And then we're going to do one of two things based off of the status of the binary search tree at the time that we add. So if it's empty, meaning there's nothing at the root, then we simply add P, which is our Pop-Tart that we're adding. We add that to the root. We do that by just setting root equal to it. So root, the variable stored in our binary search tree, references the object that we passed in. Okay? Now, if it's not empty, if the tree has at least one object in there, then we are going to call our recursive add method. All right? And just a quick refresher. When you have two methods that are the same name, but their signatures are different. Okay, this one has one value in the parameter list. This one has two. That's called overloading methods. Okay, overloading methods. And the program is smart enough to figure out which one to call based off of how you call it. So for example, in this instance here, we're calling add, and we pass it two things. So it will automatically call the add method that accepts two things. Okay? And you can do this the same way. It doesn't have to necessarily be the quantity or the number of parameters, but it also looks at the type. Okay? It's possible you have an overloaded method that simply outputs a number, and one method accepts an int, one method accepts a double. Okay? So it doesn't necessarily look at the number, it looks at the types associated with it. Okay? Good so far? All right. So here we pass it the root, which is the initial starting point, and the object we want to add. This is where we get to the add method. All right. We've commented this pretty heavily, and I'll make sure this is on Canvas for you guys to check out. But it follows a very simple process. The first thing we do is we have our subroot, which is initially root, and we have the object we want to add. And we have to determine whether that object should go down the left side of the tree or down the right side of the tree. And the way we do that is we compare the value of the object we want to add with the value at the subroot. Okay, and that's what we do in this first if statement right here. The determining value that we use for going left or right is the number of calories in the Pop-Tart. It's just what we pick. Okay? So if it's less than or equal to, we go left. Okay? Once we decide whether we go left or right, we're either going to go here or here. So if we go left, we look at this code. If we go right, we look at this code. And it's really the same thing in both places. So if we go left, we say, all right, this object P should go down the left side of the tree. Then we make one of two decisions. Okay? We say, if there is already an object at the left side, then we can't put it there. Okay? If there's not, then we can put it there, and we're going to go ahead and do that. Okay? So if there's not an object down that side of the tree that you want to go to, we simply put the object there. And that's what happens right here. Okay? Is there a child already? So if the get left child of the subroot is null, meaning there's not a left child, then we simply take that subroot and we set its left child to P. And then we're done. Now, if this is false, if there is something there already, if the left child of the subroot has an actual reference, then we can't put it there. And in that case, we simply recursively call the same method, setting the new subroot to be the left child of the existing subroot. Okay, so we simply move the whole process down to the left child, and we still pass P. Okay, that would go up to the top, and then we say, do we go left or right of that, and that process just repeats. The same thing happens on the right side. If the right child is null, we set it as the right child. If the right child is not null, then we recursively call add, setting the right child of the subroot as the new subroot. Questions on this? All right, let's peek at other classes real quick. So our Pop-Tart object, 3 values. We keep track of the calories. That's our value for going left or right for sorting in the tree. And then we have a reference to 2 other Pop-Tart objects, a left child and a right child reference. Okay? This is just getter and setter methods, accessor, mutator. And then we have our driver. Driver is very simple. It creates a binary search tree object at the top, and then it loops through and adds 5 Pop-Tarts. Notice when we call this add method, we only pass in 1 value. That's why it calls this add method first. Okay? So let's go ahead and compile. We'll run it in our Canvas window. And I'm just going to hit play, and we'll see how this goes. We can see how it populates it based off of left or right. That's it. Values that are less than or equal to go left. Values that are greater than go right. Everybody good? This is what we did last class. Any questions on this? All right. So now, let's search. Now, when we search, and if you recall, we've done traversals, we've talked about traversals, pre-order, in-order, post-order. And the deal with traversals as they relate to searches is a traversal will visit every node in the tree with the sole purpose of just outputting them all or visiting them all. Okay? We aren't searching for something specific, okay, like we do when we're searching. All right? When we search here, we're going to pass in what it is that we're searching for. You know, typically, when you're coding search methods, what you're searching for is called the key. Okay? And so when we call this search method, we will pass in what we want to search for. Okay? Now, in this case, what is the only thing we can search for? Or search by, I should say. Calories. Yeah, the only thing we can search by is calories. Okay, so we could change this a little bit to where when we randomize the object we create, we randomize the toppings or the type of Pop-Tart it is, or maybe we pass in what kind of Pop-Tart it is, and then we can search not only for calories, or we can search by type or whatever. We don't need to get into all that. We'll just keep it simple here. You have to keep in mind what you use to sort the tree, the value that is used for ordering the tree, has to be the value that you would want to search for. Okay, so when you're setting up a binary tree or binary search tree, this is important. Because if you for example, let's say we have calories and then we have the type of Pop-Tarts. Maybe there's like, what kind of Pop-Tarts are there?
Frosted on Frosted.
Is that it? What do they have, like flavors? What flavors are they?
Blueberry.
They have a s'mores Pop-Tart?
Yeah.
Why is it so amazing?
I don't
Very delicious.
They got
What?
cookie dough, they got sundae, they got brown sugar, they got peanut butter, they got peanut butter chocolate,
They have really there?
Cherry.
Unfortunately, yeah.
They got all friends.
They have like a fresh soda one.
They've got all
Like they have an orange soda one.
They have chicken and waffles.
No, they don't. Chicken and waffles Pop-Tart. Hey, that could be a thing.
That's all.
Are Pop-Tarts healthy?
No.
They're like 500 calories.
That's what I'm saying, get the unfrosted.
Give the unfrosted ones. Those probably taste terrible.
No, they got more filling. That's how you compensate. You more of the,
Well,
question.
I think there's an unreached market out there for chicken and waffle Pop-Tarts. I'm just saying, I think it could be good. How many of you would eat it?
I tried one.
Try.
Would it be like
I might not like
chicken
it.
filling?
Have a vegetarian option.
A vegetarian option? Aren't all of them vegetarian? Or chicken and waffles, you mean?
No, chicken and waffle. That's what I meant.
I think
Tofu.
All right, there we go. The new flavor is going to be vegetarian chicken and waffles Pop-Tarts.
We're on something.
I think we are. There's a small section of the population. All right, so the point of this being, if we had it set up to where we could create a Pop-Tart object and we not only specified the calories, but we also specified the flavor, the only way that we could search would be by calories. Now, certainly we could search the tree and try to find it by the flavor, but we wouldn't get login performance out of that. Okay? And the reason for that is, what makes binary search trees fast is the fact that every time you make a decision, you eliminate half of the remaining search space. So if you start with 128 objects in your tree, the first check that goes left or right, let's say we go left, we know that the 64 objects on the right side of the tree couldn't possibly be what we're searching for. Okay? And the reason for that is our tree is ordered based off of that principle. Less than or equal to goes left, greater than goes right. And so if we determine that what we're searching for is less than the root, then we know it can't possibly be on the right side. So we eliminate all of those. But if we are searching by a value that is different from the value by which we ordered the tree, then we can't use that principle. If our tree is ordered by calories and we say, all right, we're looking for strawberry, are there any strawberry Pop-Tarts in our tree? And we look and the root value is blueberry, we can't conclude that if there were a strawberry object in the tree that it would be down the left or the right side, because we ordered based off of calories, not by the flavor. Does this make sense? Okay. And so the point I'm trying to make is, this is aimed at the practical application of binary search trees. You know, when we're setting up a simple example like this, it's really easy. But if you are actually implementing this and you have a complex object that's more than just calories, left, right, child, then you need to choose an appropriate ordering value so that you can take advantage of the search. Okay? And you should use binary search trees when you need to search your structure frequently. Okay? This is the only structure that we have gone over that allows you to search quickly. All right, we good with this? So let's get into coding. And so what we have to do, because we set up calories as the basis for our search, then we have to search by calories. All right, so what I'm going to do, just for the sake of simplicity, I'm going to go to Pop-Tart, and I'm going to change this. Instead of having it randomized between 1,000 and 1,100, or 1,000 and 1,999, I'm going to decrease that variance down to 25. So we'll get anywhere between 1,000 and 1,025 calories. The reason for this is just increases the likelihood that when we search for a value, it's within what we generated. Okay. So let's go to the driver. Let me save this. And we'll say, we'll search 5 times. I'm going to increase this. Let's add 20 objects to the tree. We'll search 5 times. All right, so we'll say system.out.line pop tart tree dot search, and then let's search for. We could randomize this, but we don't. We don't need to do it for it. So we'll see if we have those. We'll just do 3 searches and see if we can find 1,000, 1,010, 1,020. Okay. See if we have any Pop-Tarts in our tree that match those calorie values. So now that we know how we call it, notice we do 2 things. When we call search, we pass it the key, which is the value that we are hoping to find in the tree. Okay? 1,000, 1,010, 1,020. We know we have random calorie values from 1,000 to 1,025, so we'll see if we get lucky. Also, we call this method inside of a print statement. And so this tells us that we expect to output something. Whatever the result of the search is, we're going to output. Okay? So we need to decide, should we search and have it return true or false? Yes, it's in the tree. No, it's not. Or should we search and have it return the object, or null if it's not in the tree? What makes more sense? Practical use, what makes more sense? What would be better, true or false, or an object reference? All right, so the answer to that question, and I should say this, a lot of times when you're trying to decide stuff like that, you have to ask yourself another question. And the question you should ask yourself is, why would I be calling search? And when I call search, what am I going to do with it if I find it? Okay, so why would we search this tree? Or practically speaking, if we had an actual program or a game or something like this, why would we want to search a binary search tree? Any ideas?
To find that object and use it.
Yeah, exactly. To find an object, if it exists, and use it. Okay? Generally speaking, when you search a data structure, you don't just want to know whether or not something is in it. Okay? You want to do something with it. Now, it might just be outputting information. Okay, so let's say we run a small business, and we want to keep our inventory in a binary search tree. Probably wouldn't, but you might. Customer comes up to you and say, hey, do you sell XYZ? I don't know, I'm just the intern. So you type it into the computer, and it searches the tree, and it says yes. And they say, where do I find it? You say, I don't know, it just says we have it. Okay? Or the program says, yes, we have it, here's the item information. It's on aisle 4. It costs this much. We have 8 in stock. Bless you. Does that make sense? So, moral of the story, when you search for an object, you're better off having it return or reference the object. If you don't find it, you simply return null. The only caveat to this is, before you do anything with it, you have to make sure that it's not a null reference. Okay, that's not going to bother us here, because if this returns null, it will just output null. But we can't say pop-tart-tree.search this and then .toString. Okay, because that would give us an error, because we can't call toString on a null reference or print out item information. We can't do that. Okay? You have to make sure it's not null first. All right. So now that we have this, let's go over here. And we'll have public Pop-Tart search int C. C for calories. Is this confusing to you guys when I use short variables like this? Would it make more sense if I put int calories?
No.
Good. Okay. That's how I normally code, but a lot of times you will, as a programmer, develop little idiosyncrasies that make sense to you, but don't necessarily make sense to other people. I always use short variables like this for parameter variables, or like local variables that you pass in. And when I see that, I know in my head, if I coded it, that it's like just a local variable that we passed in. Okay? You do it if you want, but that's what I do. So we're searching for C, and let's figure out, so searching for a Pop-Tart with calories, wow, C-A-L-O-R-I, calories equal to C. So, do we think this is going to be a recursive method? Yes. Are tree traversals recursive? Anytime that you need to visit nodes in a binary search tree, or any binary tree, it's going to be recursive. That's how it goes through. Okay? So what we want to do, the first thing we want to do is make sure that our tree is not empty. Because if our tree is empty, then we can't begin the search process. So we'll say if is empty. Notice if we do the same thing up here, we're simply going to return null. If the tree is empty, then we return null, because it's obviously not there. Now, if the tree is not empty, then what we're going to do is we are going to begin the recursive search process. So just like we saw a little bit ago, we're going to see the same thing here with the add method. I mean, here we are going to say search, passing the root and C. Okay. Now, go with me. Void, Pop-Tart, search, Pop-Tart, subroot, int C. Now, there's a mistake up here. I left it in on purpose so you guys can catch it. Now, if the tree is empty, we return null. There's no need to have an else statement, because if this is true, then we automatically stop the method. We automatically return. If this is false, then we skip this and we're automatically going to come back here. We're searching, so we're going to call this search method, passing the root as the initial subroot and C. This is the same thing we did above with the add method. There's an error with this. What is it? This won't compile.
You had to do something.
No open bracket.
Open bracket. We don't need the open bracket. We could put it in there. It's only one line, so we can leave it out.
The name of the method. There's
No,
no public or
return
private.
It doesn't have to be public because we're leaving it here. Okay, and we're calling it from here. This one has to be public because we're calling it from the driver, but this one doesn't because we're calling it here.
The return statement?
Yes. It's missing a return statement. Where?
Not the search.
Not down here. Well, yeah, this won't.
No, I'm saying like underneath search. Yeah, right there.
Now, watch what happens. Does this search calls this, right? Does this return something? It should. towards the Pop-Tart. So when this finishes, where does this return its Pop-Tart that it found?
To public service.
Right here. So watch this.
Whoa,
Did that break something?
mind blown.
We're returning a method call. We know that this method returns a Pop-Tart eventually, or null. Either way, when this finishes and we come back up here, the ultimate return happens here. Okay, we good? That's kind of confusing. So, what we put in here is going to look similar to what we put in the add method. It's the same process. Okay, we're going left, we're going right. Is there something there? Yes? Okay, well, good on there. But at any point in time we hit it and there's nothing there, then we know it's not there. Okay? The same process, but what we do during the process is a little bit different. All right. So, because we are looking for something, whether or not we go left or right is the secondary decision. Okay, the first check is what we're looking for at the subroute where we are now. Okay, so that's the first check. We know there is a subroute, so we're going to say if C equals subroute dot get calories did we find a match? If we did, what do we do? What do we want, not code-wise, what do we want the method to do?
To return that object.
Yeah, to return the object if we find it, right? Did we find it? Yeah. How do we return the object? Return subroute. Good. Now, if we didn't find it, the next choice is, do we go left or do we go right? If it's not at the root, then the value is either less than or greater than. If it's not equal to, it has to be less than or greater than. Okay? So, else if C is less than subroute.get calories, if it's not equal to, and it's not less than, by logical definition, it has to be greater than. That's good enough. So there's no need to do an additional else if. There's no other possible solution. All right, so if comments are good. I'm gonna So if we go down the left side of the tree, we're faced with another choice. Is there a left child? If there is a left, well, let's do this. Let's write the code to determine if there is a left child. If subroute dot get left child equals null, if there is not a left child, what does that tell us?
You have to go to the, oh no.
If there is not a left child, what does that tell us? the college is not what? Right. It's not there. If we determine that it should go down the left side of the tree, and there is no left child, that is not in the tree. Because if it were in the tree, it would be there. At least somewhere down that side of the tree. Right? And so we simply say, what do we do?
Isn't that a return? No? Yeah.
Can I have Pop-Tarts? Return no. It's not there. Return no. Else. Now if we hit this else statement, that means there's still hope. If there is a left child, what do we do?
Recursive call would be so we get left child and
Correct. So here we say search, setting the subroot to be subroot dot get left child. Let's see. Is that right? Don't say yes. Why?
because you can't put that in.
Sure you can. Well, we want to keep searching the left side because we determined, based off of this, that it's on the left side. So, walk with me. We're searching, we start at the subroot, which is the root of the tree, searching for C. First check is if the value of C, what we're searching for, matches the calorie value of our subroot. That's what we do right here. C equals subroot.get calories. If this is good, then we found it, we're awesome. Return and we're done. If it's not, then we check to see do we go down the left side or the right side. And what this does is this basically eliminates the other side of the tree. Okay? So if this is true, let's say this is true. So our calorie value is less than the calorie value of the subroot. So we're going to go down the left side of the tree and we know that it couldn't possibly be on the right side of the tree. We check to see, is there a left child? So we determine we need to go down the left side of the tree. If the value is in the tree, it's down the left side. We know it's not the root, it's less than the root, so if it's there, it's got to be down this left side of the tree. And so the first thing we do is we look at the left child of the subroot. And we look, is there a left child there? If there's not a left child, that means there's nothing on that side of the tree, and we know it can't possibly be there. So we return null. If there is a left child there, meaning left child or get left child is not null, if there is a child there, we don't want to search that value at this point. We want to recursively call search and move the subroot from the existing root down to the left child. And we recursively start the process. Because the first thing we do inside of the recursive call is we check to see if the subroot equals C. So we're going to check it as soon as we get down there. Okay? And then we repeat the process. Because we could go left and then right. But there's an error here.
Do you have to set a temporary root or something? Like a subroot?
You need to return it. Very good. Everything must get returned. So each time we make a call, it's got to get returned. Because if we make 3 or 4 calls, each of those calls has to be put on hold because when something gets passed back to it, we need to be able to return it to the one above it that called it. Okay, so that process has to continue. I'm going to copy and paste this and change this to be the right. Let's see if it works. binary search tree out of 20 objects. So we've got to let it populate itself. Okay.
Quick question.
Yep.
Would you want us to stipulate if there's like the same value? Because I see 1,011 like 3 times. Is that like important or?
In your program, remember you can't have duplicate values. You'll just increase the frequency. So if this were your program, instead of having 110 appear a few times, you would have a single 110 object, and then you would have a frequency variable on the object that would have a value of 3. That's what you do. All right, so we're here, and we are paused on our search. Okay, and we are searching for 1,000. Okay, searching for 1,000. So we hit this. Notice we hit our search method here. Checking to see if it's empty. It's not empty, so we're come down here to the search method. Okay? So this is where we call the recursive search method, passing the root as the initial subroot, which would be 1,015, and our calorie value, which we're searching for, which is 1,000. So we see it's here, and we'll see if we can find it properly. All right. So did we find a match? This checks to see if C equals the calorie value of 115. So we get the calories. It's not a match. So we check to see, is it down the left side or the right side? Okay, so we grab the calories again, and we determine that it should be down the left side, because 1,000 is less than 1,015. So we determine that it should go down the left side. And once we make that determination, again, this tells us that if the value is in the tree, it is not down the right side of this subroot. So it couldn't possibly be over here, because all of these values have to be greater than 115, or 1015, okay? Which is accurate, okay? We know it can't be here because we're searching for 1,000. So we check to see, is there a left subchild? There is, it's 1010. So we recursively call search on that, okay? So notice the subroot now points to 1010, and we repeat the process. Does 1,000 equal 110? It does not. So do we go left or right of 110? 1,000 is less than 110, so we go left. Okay. Is there a left child of 110? Yes. And again, when we made the determination that we're going to go left, we eliminated the entire right side of that subroot. Because all of these values are larger than 110. Because we're searching for something that is less than 110, it can't possibly be here. So 2 comparisons, we've eliminated all of this and all of this. So there is a left child, it's 1,002. So we'll set that as the new subroot. Notice how we keep moving down the tree. Right? Now, compare the values. 1,000 does not equal 1,002. So we check to see if there's a left. So we're going to go left, so we immediately eliminate all this stuff. We got 1,002 again. Check to see if it's on the left or the right side. It should be less than. Is there a left child? There is a left child, so we call this again. We've then set 1,000 as the subroot, grab the calorie value, and we say, hey, these 2 finally match. So we return the subroot. Now here's what happens. What we have is, we have 1, 2, 3, 4, 5 recursive search methods on our stack. Okay? All of the above ones are on hold. And so what we're going to do is we finally found a match. So we're going to take this and we have to return this up to here. That returns it to here. That returns it to here. That returns it up to the top. The top returns it to our drive. Okay? So you'll notice we just hit this and it returns here, and then it returns back to the same place, and then it does it. If you notice, I didn't have to click it 5 times. It's because the compiler has some optimization things built into it when it comes to recursion, and it knows, it identifies the pattern that you're just returning it over and over again, and it kind of short circuits back out. Okay? So if we look at the output window, we'll see that we found it. We just call it two-stream method. Same thing with 1010, goes much faster. We find it right here, and we're done. And then we search for 1020, which we have that as well. And you can see that we can find that too. That's it. Questions for me on this?